Okay, here is the famous fundamental theorem of calculus. So we will let f be a continuous function, doesn't need to be differentiable, just continuous. Continuous on the closed interval from a to b. Then this accumulation function, capital F, right, the definite integral from a to x, and again, x can be anything between a and b. This thing is continuous on the closed interval from a to b and differentiable on the open interval from a to b. And moreover, when I take the derivative of this thing, I get back to where I started, right? So the derivative of the integral is just the function. In other words, in some sense, the derivative will cancel with the integral. So the only thing you need to do whenever you get the derivative of an integral is just replace t by x, and then that'll be it. So this says that the derivative will cancel out the integral. And we'll see later on that the integral will cancel out the derivative in the same way. All right, before we write down a proof of the fundamental theorem, and I do think the proof is kind of instructive because it's a good review of the stuff we've learned. Let's make a quick observation. If you look at an interval from x to h and then look at a function that's a continuous function that's defined on the interval from x to h. So here you've got the value of the function f of x. Here you've got the maximum height of the function on this interval. And then here you've got the minimum of the function on this interval. Now, what happens when you move h close to 0? When you move x plus h close to x? Keep the same function, but now move x plus h close to x. Well, when h is small, in other words, when x plus h is close to x, what happens with these three values? Well, they all get closer and closer together. So, when x plus h is extremely close to x, right, there's not much difference between the value of the function, the maximum of the function, and the minimum of the function. So when h is small, these three things are roughly all the same thing. Okay, here's a quick proof of the fundamental theorem. So here's the difference quotient, capital F of x plus h minus capital F of x over h. So the reason why we're looking at the difference quotient is because we want to compute the derivative of capital F. And here's capital F. So what is capital F of x plus h? Well, everywhere I see an x, I'm going to write an x plus h. So now this is the integral from a to x plus h. And then minus capital F of x. So that's just minus the integral from a to x. So you've got the integral from a to x plus h, and then you've got the integral from a to x. And so when you take the difference of these two things, so this thing minus this thing, you just get the integral from x to x plus h. So the difference of these two things, that's just the integral from x to x plus h. So now, what about this thing? Well, remember, we can bound the integral in between the maximum and the minimum times the length of the interval. So, right, the integral here is going to be between the difference of the bounds, so x plus h minus x, that's just h, and then we multiply by the minimum of the function. So let me call that little m of capital H, because the minimum depends on where h is at, right? The minimums and maximums will change as you move h close to 0. So this thing is less than or equal to the integral, and then, right, if f is less than capital M of h, then that means the integral will be less than the difference of the bounds times capital M. So just remember that theorem that we had if a function is bounded between little m and capital M, then the integral is bounded between little m times b minus a and capital M times b minus a, right? That's just a theorem from a few videos back. So that's how we got this statement. Okay, so now I can just take this inequality and divide everything by h, and I'll get back to the difference quotient that I started with. Anyway, so now we've got 1 over h times the integral. That says the difference quotient is between these two things. But now remember what happens as h approaches 0. So remember, we want the limit as h approaches 0 in order to get the derivative. Well, as h approaches 0, the maximum and the minimum and the function all start to converge in on the same thing, right? So as I move h close to 0, the max and the min all start to look like f of x. So this thing goes to f of x. This thing goes to f of x. That means the thing in the middle has to go to f of x by the squeeze theorem. So the limit as h approaches 0 of f of x plus h minus f of x over h, right? That's just going to be, according to the squeeze theorem, f of x. Right, and so this thing, this is actually the derivative. So this says the derivative is equal to f of x, and that's what we wanted to show. So that'll do it.